unsupervised learning. Just a few maybe logistic remarks. So hopefully everything is going well with the project too. Hopefully you found a group and also a topic. Maybe don't hesitate to ask questions on the forum, right? So also if you have technical questions about your specific project, then ask us in the forum so we can really help you. That if you have machine learning questions which are not on the domain but general, then ask them in the forum. And also for the domain specific questions with your advisor. And also if you do any of the other challenges like the reproducibility or the standard challenges. Yeah. Okay, and I just uploaded the slide right now on the GitHub. It's there. Sorry for the delay. So slides today will cover a small intro to unsupervised learning. And then in the second part also to talk about clustering. And yeah, are there any questions on the logistics or exercises and so on? All good. Then let's get started. So what we've done so far was often the very standard kind of learning that you already gave all the true answers to the system. So in every learning step, you were telling the system it predicted something, but then you told it, hey, no, you need to predict this other value, the true label. So, but maybe it's fair to say that's not really how realistic human learning would work, or how a child learns. It's not really like that, right? It's maybe fair to say that the vast majority of what we learn as a human is not because someone gives us the true answer, but it's by observing things ourselves, right? We just observe what happens. We don't always get the thing that we are supposed to do as an answer, right? Sometimes we just observe things happening in the world, and we're trying to learn from that. So we just, like, if you just watch a video, nobody is going to tell you, annotate every frame of it, that this is a bird, this is a ball, this is a table. But you're just watching the video, you have to figure it out yourself. So is that also possible for machine learning, that what to do if you don't have all the labels available, these true answers? So this is unsupervised learning, and it's quite difficult. In general, there's a million ways to do it. So there's not like one right way to do so, but it's also has also huge potential, because it also allows us to tap into like vastly more data compared to what we have gotten annotated from someone. I mean, if you use supervised data, it's so tedious and so much work because a human has to look at every data example and give us the true answer for it. So that was extremely work intensive, and it's human work intensive very often. And here, if you get rid of that, if you don't need these explicit labels anymore, there's such an opportunity to work with, I don't know, 100,000 times more data, which is maybe available. I mean, it's surely available. The question is, can we learn from it? So, and yeah, it's not so useful to formalize it much, but what you can say is you just have the access. You don't have any whys. So no whys today. Only access, which are our observations. So yeah, that's the goal. And why would you do that? Or what are different ways to do it? Maybe, so I mean, this is not a precise categorization, but surely two very important aspects to do it is to learn a representation. So this means to learn features. So learn meaningful features for the things, the data points that you encounter. So which are, yeah, features which are useful for something. So maybe they're useful for machine learning you might do later on, maybe for supervised learning, for anything. Something which is more useful than the raw pixels of an image. Something which has the meaning and logic of this data point represented in a better way than if you just use the raw data. That would be to learn good features or to do representation learning. And question is, can we do it unsupervised? And that's one approach. And the other approach I would say is to ask, can we generate data? So can we surely have data, right? But we don't have any Y labels. But what you can also ask is, can you just teach a black box to generate more data, which looks like real? So that's the idea. Generate fake data that looks as good as the real data, that data set that you were given. So these are generative models, right? So train a system which from some random number, some very small noise value, can generate any data point which looks like real. And again, can you do that in an unsupervised way? And it sounds plausible, because it's certainly not something which depends much on the labels. And then there's a variant of this, which maybe we can also mention, which is density estimation, which is maybe just to better understand this manifold of real data. When someone gives you real data, then you're trying to understand, if you think of this as a probability distribution, so among all the things can happen, which ones are actually real images? And you're trying to understand how is this distribution, how is it shaped? Like in some parts of the space, there is certainly no real images. In other parts, there's a lot of real images. So can we describe the space of real images or any other data? Of course, there's nothing here specific to images. It can really be for any data modality. So that's the high level idea. And yeah, we need to make this more concrete. But yeah, I would say that's the key part today, is that we have no outputs available, and that will also keep us busy the next week and after, to see a few methods which can do data analysis without having outputs, and to also see them in a hopefully a bit unified way. So okay, let's see some examples. So I will not go very formal, precise with these examples. So actually some of them we will come back later. For example, recommender systems, we will come back. So this, you have actually also seen this at the very end of the ethics lecture on Tuesday, that recommender systems can also have very interesting implications. And what it is just to learn an assignment between people and items or products. To learn which one of the people might like which one of the items. So, and that's something that we will surely look more into. And for example, yeah, this matrix you see here is movies. Every movie is like a column, and so what you have shown vertically is these features which are learned, such that then when you ask like this particular movie, I have this column here is the features which I learned from this movie. I can take that, that's like what we call this kind of movie vector. I can take that movie vector, which is part of this matrix, and multiply it with a user matrix. So this is the user, and this is the movie. So this dark line should be the feature vector, and you wanted the inner product of these two sets of features. You want that to be how many stars did you give to that movie? So that's the idea. Let's see. So yeah, this feature, let's say the feature vectors are green, then you wanted the feature vectors explain how many stars you give to that movie. And this is also very related to other kind of matrix factorizations, which we will also discuss in 2 weeks. For example, mathematically, the very same model is also used to learn representations of text. So of words, for example. Which words appear together? So are there features which can explain that for every word you will learn a vector? So can you do that such that the vector feature for the word will explain how it appears together with another word? I mean, how often it appears. So then if you can do that, then you hope that this vector captures the meaning of these words, which it actually does, which is called this word-to-vec method, which we will discuss in 2 weeks when we discuss NLP. And mathematically, it's exactly the same thing as a recommender system. And if you do it for the words, and it's also very nice because it's clear that it's completely unsupervised, because the words, you found these 2 vectors, you found them just to produce how often the words appear together, right? And that information is just there. It's not that somebody has annotated it for you. It's just that in all the text in the world, these 2 words appear together very often, and those other 2, they don't. And that's the information you learn from. So it's a pattern which is already there. You don't need a manual supervision. So that's to introduce representation learning. And it's a bit debatable if the recommender system is also unsupervised or not, because people at least gave these star ratings. So, but we will get more to that later. And here is another type of data, it's just trying to understand data from all individual villages and towns in Switzerland. So these are, I don't know how many, maybe some 1,000 or so villages. I know in the US there are 3,000 counties. In Switzerland, maybe less. But you can try to analyze them. And here what we look at is the voting pattern of each county, or each town. There's every few months there's a referendum, people vote on something, and then this village will vote a bit differently from that other village. But what does it mean, right? We don't want to use annotated data here. We don't know the meaning of these votes or these events that I think maybe it's 200 votes which have been done by every city here. And can we still understand if these different villages vote completely differently from others without understanding what the votes actually mean? And so for every village, we have a 200-dimensional vector, which always says like yes or no, which is set for each vote. But we cannot easily visualize 200-dimensional data. So what is done here is a principal component analysis, which is also something that we will discuss next week, because it's really similar to other representation learning techniques like word-to-vec and other things. So now people are more familiar with word-to-vec than they are with PCA, than used to be the other way around, but they are almost the same. So anyway, what was done here is that, yeah, so number of villages times 200, which is the number of votes, that matrix was taken, and then the 2 first principal components were computed, and then we only have 2 features per village, and that's the colors that you see here. So, and these 2 features, they are trying to explain the biggest directions or the biggest variations that are present in this 200-dimensional data set. And you can see that if you do it, then you actually see a bit more clearly that yes, there is systematic differences here, for example, between the German-speaking and the French-speaking regions, and maybe to some degree with the Italian-speaking one as well. So this is a principal component analysis, and we will get further, more formally into this later. So just a teaser, so to say. Then, but the cool thing again, completely unsupervised. We don't need to understand anything about these votes. We can just take the matrix which is there in nature and basically factorize it, and we are done. No labels needed. Here is the same thing again. Principal component analysis, which you'll get to. It's applied on a very different data set. You can do this in biology. For any kind of organism, you can take the genome sequence of each individual. And without knowing anything about these individuals, you can just take this genome sequence and then do a PCA on all these people, which are all in the same database. You have no idea about the identity or any side information about these people. just the genome sequence, and then you do PCA on it. Again, the first two principal components, and then you see, you look, every data point is represented by the two first principal features, and they interestingly seem to also mimic some reasonable patterns. There was zero geographic information used in this data set, but using PCA, you can discover that there are patterns in the data, and it's easier to understand two-dimensional data than it is to understand a million-dimensional data, or well, a genome is even much longer than a million features. It can be many more of that. So, but it's just an example, so we don't want to get into the domain-specific aspects here. So that was basically dimensionality reduction, the two things I showed you, or three, if you even the recommender system and text as well. Here is one which is a bit different, which is clustering. I'm sure all of you have heard a little bit about clustering. It just means to group data together. And this example here is a hierarchical clustering, which means some groups are then again grouped into bigger groups. So for example, here and then here and so on. So this is a hierarchical clustering of, again, biological data sets with human microarray data, which is also related to not the whole genome, but just very few specific positions. And then from that data, it's also not so clear what is the precise meaning of each feature. But what we can still do is we can say who is similar to whom, right? Here it's about cancer probes from biological tissue. And then the closest ones, you group them together, and then you can also have more grouping. The grouping is just defined by a similarity function, which is usually just the Euclidean distance, where you can use other similarity functions, and then you can form a grouping or a clustering of this. And that's what we're going to discuss in the second part of today. Not the hierarchical case, but the standard clustering methods and algorithms here. So yes, just a few examples. Clustering is really widely used for all kinds of applications. So here it's about scientific text. You can use it to text is also very high dimensional data, which is very difficult to understand every particular aspect of it, right? And very often you have text without clear labels for what you are interested in. So text is high dimensional, and there's a lot of it. So it's a perfect application domain for unsupervised learning. And maybe the very easiest example of unsupervised learning is just to do this clustering. You can see that it does. These are some older papers, right? But it really can help you to get a better overview. If you have a very large data set, you cannot look at every data point manually. Then clustering can help you to get an overview, and then maybe once you have these groups, then it's easier for you to do something further on, maybe to decide what you want to do, or to do some supervised learning afterwards, or to use these cluster names as a feature for other purposes. So there's many options what to do with it, also for data exploration. So yeah, that's clustering. Of course, only this is only text, but there's many other data modalities you can do it. Then maybe I'd like to spend just maybe 10 minutes or so on some more advanced applications of unsupervised learning, which are a bit more related to deep learning as well. And there's really a lot that has happened in this area in the last 10 years or so. So it's quite amazing, right? Because clustering is much older. It's always existed, and the same for linear dimensionality reduction. We all kind of know that. But there's a few very interesting techniques which have become much more impactful and more common now that we have deep learning. And it's not so much about these architectures and so on. It's really the key ideas here is always like, what do you learn from, right? What do you want to predict from what, such that it helps you learning something. So it's not about how many layers you need, but what is the signal you can learn from? And one, of course, very kind of obvious idea is to do compression and reconstruction, which just means that, okay, maybe I try to squeeze my original data into a smaller representation. For example, you have this one image going in on the left. It goes through a bunch of layers, and then you have a smaller, a more narrow layer in the middle. So, okay. And then from there, you can again go back to something which is the image space. So you can again, from this smaller number of features, see, is there a network which can take these intermediate features here and expand them and generate an image again, right, which looks like a real image. And I mean, this is just an architecture, it's nothing special, but the key idea is, again, the learning signal. How do we train this? How would you train this if you don't have labels, right? And the really smart idea here is to just say that I want the output image to be as close as possible to what was the original input, right? So that's the reconstruction. So you just say, okay, here is a reconstruction error. It's quite natural. And let me try to train my deep net now to find weights such that this reconstruction error is as small as it can be. Where the reconstruction error, you can just define it on every pixel. So how Euclidean distance, or that's actually the most common loss that they use, just use a least square loss, or L1 loss is also used sometimes. Okay, so you just train this network to reproduce all the data again, which sounds a bit pointless. But the cool thing is that once you have it, then because this inner part is so much smaller, and you will only have like maybe 100 features here, and the image might have 100,000 features. So now you have found 100 features from which all of the information of the image is in these 100 features, because, well, here's the proof for it, right? It's able to reconstruct the image again. So it's really just, it's nothing special. It's really just learning two functions. The compression, or sometimes people call this the encoder, is the left part, and then you learn the reconstruction, which takes the features and reconstructs something as close as possible to the original image. That's what people call the decoder. So encoder. So if we're writing, and the right one would be the decoder. But again, the important thing here is the loss function. So what's the signal we learn from? So this is an autoencoder, and this can work quite well in some cases. Really depends a bit how you train it and if it learns something meaningful or not. There is even better representation learning techniques now, which are more related to something like contrastive learning. So I'll explain in a second. It's also quite a simple idea. But just to say again, the main goal is to learn features, right? So this is for representation learning at the moment. So thus there exists a small number of features which capture all the meaningful information from one data point. So, and here I found my 100 features which do this job, which is very nice. So we'll have the same goal also here when we do contrastive learning. It's just that there we use a bit of different learning signal. So actually this is kind of in contrastive learning, you will only use an encoder. There's no decoder. So there's only the left part of the neural network. So here's the image. It goes into your net, and then there is a few neural networks layer, and then outcome is maybe the 100 features, or as many as you want. But so this is called the encoder-only architecture. So how could you train this? So there's no reconstruction loss here. So there's no image which is generated. Do you see a way to train this network here with some meaningful loss function? We don't have any labels, right? We need to define a loss function only from the data we have. So sometimes what we do here is we try to define in a natural way that some images, they should have similar features because we know that they're similar. So for example, here are two images which we can just be sure that they're similar because it's not because someone has told us it's a dog. It's not that. It's just because the lower part is a part of the image of the original one. So you can say, when you have a big image, then of course also all the small parts of that image, they should have the same meaning, right? They still have the same meaning. It's still a dog, right? It's just cut a bit in the middle. Yeah. Is there a question? Yeah. Yeah, you're saying I could just use the distance between two images and try to keep it small also when they're actually similar images, right? But the question is, in which space do we compute this distance, right? If you do it in the image space here, it's very difficult to say. Maybe one other image is just shifted by 1 pixel, so it's not obvious to someone if two images here are similar. But what we're doing is that actually that's what we train the red features to be. We train that the red features have this property. We train that those features have the property that similar images should have similar features, right? And then hopefully the network here will learn to do this job, right? To understand that, yeah, when an image is just shifted a bit or something is cut off, that then the features should still be similar. And that's actually what we use as the loss function, right? That the loss function is exactly defined here, that images, two of them which are similar, so these are the two here, they must have close features in this feature space. The feature space is just very small, only 100 features. So in that space, Euclidean distance between two positive images, that's how we call them, right? The ones we know are the same, they should be close. It's a bit similar. You could do this for words as well. If you know that two words have the same meaning, then they should be close in their features. So, but we don't know if two words have the same meaning, so it's a bit harder there. So, yeah.
Yeah, that was my question. How can you know in advance if your two images are similar or not, and measure if they're embedding this also too?
Yeah, that's a great point. Like, how do we know that two images are similar? And you're right, we usually don't. But what people do here is that they just do some smart tricks to circumvent this. They just, from one image, they just generate some meaningful transformations, which are still saying, if I rotate my image, for example, then you would agree that it should still be similar, right? It has the same meaning. If I shift it, if I remove half of my image, then it should still have the similar meaning, right? So so there is kind of transformations that people, this needs a bit of domain knowledge, right? So for words, I have no idea how to do it. So, but for images, people do this, and there it works really well. There's quite some natural transformations you can do and say that, yeah, then the image should still have the same kind of meaning. And also it's very robust, right? It doesn't need to be perfect, right? You will get many of them will be wrong, but it doesn't matter, right? You will still learn a very meaningful representation that the features often will carry the meaning. So how to get this positive? So these are some transformations of real images of this one anchor image, which we have fixed, and transformations. And then the other part is the negatives, right? So here, that's easier, right? Which images do we want to not be close, right? And here it's super easy. So if you just take any image of the world, which is just not the one you had, right? There's billions of images, and you just take a random one, right? The chance that the random images here is exactly the same meaning as the image you had in your hands here is almost zero, right? So you just use these negative samples, which how we call them, yeah, images which you're pretty sure that they have nothing to do with your current image, and those you want to be far. So those in Euclidean distance have a red feature vector which is far away, and the ones which you think have the same meaning, they should have a feature vector close, and that's how this encoder-only neural network can be trained. But still, there's a lot of research work going on here and trying to find variations of such techniques to find better transformations and do different ways to do this, sample the negatives and the positives. So this is not it's not an out of the box finished thing, but it's really nice and kind of powerful, because certainly we have not used labels here, but it needs some domain knowledge to understand, yeah, can I at least have some similar data? And then, yeah, actually, you know, a lot of the deep learning work started a bit in 2012 when there was this ImageNet kind of, they call it the ImageNet moment, right? When deep nets were the first time really getting much better performance than the traditional methods. I mean, there's many. It was kind of a gradual thing, but still happened within 1 or 2 years, quite quickly. But then everything was completely supervised. So there was nothing like that, right? There was only, okay, it's not completely true, but so most of the methods were supervised by this. The ImageNet dataset has been labeled. This is a cat. This is a dog. This is, I don't know, there are actually 600 types of dogs or something in that dataset. There's 1,000 classes. That would be a lot of dogs. I don't know. So there's lots of. What I want to say is that everything was just based on these human labels. And here, this is different. So what we can do now is, so this whole part here is trained completely unsupervised. And then we use those features, the red ones. And then from those features, hopefully you will have a much easier job to solve a supervised classification task, such as ImageNet. So you just take this unsupervised task, you take those unsupervised features, and then on those, you might still need a few labels for whatever you want to do, but you might need much fewer labels, right? You could just use a very simple model on top of these features. Maybe just a linear classifier on top of this. That's actually what is done nowadays too. You can get almost the state-of-the-art performance on image classification by a very smart technique like this. And then after the red features, you only attach a linear classifier, and that's all. So it's kind of restricting yourself that you want to use as little supervision as possible and see, can you still learn, right? So it's actually, this is much more interesting, right? What we're asking here is, can we learn from fewer labels? That's a more interesting question than, can we learn from a bigger data set, right? So it's actually, if you get the same accuracy on the same data set, but you have used much fewer labels, it's a very cool result, right? That's very impressive if you get, yeah, state-of-the-art ImageNet accuracy, but you have only used 1/100 of the labels that were there, right? That'd be nice, because then you need less specialized manual supervision. So, okay, this is just the idea, and this is contrastive learning. You can also do this in videos, for example. In a video, it's also quite clear that the frame at this moment and the next frame and one step in the future, they should be similar, right? And then a completely different frame from an hour away in the same video is maybe not going to be similar. So those use as your negatives. And actually also in words, okay, I can correct myself now. I know there is a way to do this for words. So you can say that the words which are next to you, they are related to you, and the words which are very far from away from you in a text, I mean, when they're like on 2 pages further in the book, then this is a word which is not related to you, right? So there, it's actually the same technique which is used to learn feature vectors for words in Word2Vec. It's the same thing. You just say the ones just next to you, they count they must have similar representation to define you. And the ones which are far away in the text, in 3 pages later, they don't count. So they are the negatives. So this idea also can be used for text in sometimes. So we will actually get to this in 2 weeks. Okay, so this was representation learning, just to give some idea, right? The dimensionality reduction was also a case of that. But then let's not forget that this is one other main technique, we mentioned it, which is generation, which is completely different from us here. You can just ask, can I learn a neural net to generate data which looks like real? So that's a bit a different idea. So this has nothing to do with the part here. So here we certainly don't generate any data. Although here we kind of do, right? So here, the second part is actually able to generate data. So you have gone to the features, and then you can use the reconstruction network. So that from any features you give it, it's able to produce an image, right? So that again is a bit like a generative model. So this, and we will discuss a few more of these as well. So, okay, generation and representation learning. To summarize a bit the examples we have seen. We have seen the autoencoder, right? There's a few more variants on it. So, and what I want to do here is I just want to emphasize some of them can be used to generate data, and the others, they're just here as representation learning. It just means that they give you very good features, but maybe these methods do not generate fake data. So we discussed representation learning, right? On images, video, and so on. So text and also time series is also very nice. I think it's an interesting field. Can you, if you don't know anything about the time series, so much time series data is around, right? Anything that happens is often happening in a modality where there's a time component. Sometimes you have data at a regularly space-time interval, sometimes not, sometimes very irregular. So I find time series also quite interesting if you can do some kind of representation learning on that. Again, usually you don't generate something there. And then language models. This means this is a particular type of, this is a model, whether a neural net or any kind of model, which generates text word by word. So you give it a few words and then it can continue the text. So that's a language model. So those are also generative models. And other models which take sequences of words and maybe translate it to another sequence of words in a different language, which are also kind of generative models because they can generate language. So, and finally, we cannot finish this first hour without mentioning GANs, so generative adversarial networks. So this is really maybe nowadays one of the most common ways to generate data. And it's pretty cool because it's such a simple idea. So again, can you teach a network to generate data if you don't have any labels? So how would you do that? How can the network learn what is real data and what is fake? And this is, you might say, why do I even care about real or fake, right? But this, if you look at this, there's so much structure, which is the images we have, natural images, are so different from just random points in that space, right? It's vastly different. I mean, if you look at an image, it has a million pixels. And if you look at the same million pixels, but they're just randomly filled, it's not the image which makes any sense, right? So there's so much hidden structure about the world which is there when we talk about images, photographs, right, of something. But how do you teach network that it can do that? It can understand to generate some realistic looking images and not just random noise. So, and the way you teach it, I mean, it's a bit similar to this. This is also a bit like the close ones versus the arbitrary ones. So here we will do something similar to train a network for real against fake. And so, yeah, I don't have much space to draw here. But it's really simple. You have a generator network which outputs an image, and then you also have the real images. Someone gave you a data set, a bunch of real images. So you have two kinds of images. One's from the real, and one type of image is these fake ones, which generated by this generator network. But how do you train the generator network? So the trick here is to use another network, so that you kind of have this game situation that two learners interact. And that's also a really beautiful idea, that so some learning can be done by providing additional interaction, right? Interaction a bit more non-trivial than just give me a label, is this a cat or a dog, right? So, but something a bit more interactive here. And the game is simple. It's just a generator generates the image. Discriminator has to tell, is it fake or real? So, and if you do a bad job as a generator, then it's very easy for the discriminator network to do this correctly, right? So, and the point here is that these two networks are trained together. So the generator tries to fool the discriminator, so there's a low performance, and the discriminator tries to have a high performance in detecting the fakes. And this is just added up. These two objectives are competing. So this is the game, right? The generator tries to find the best weights for his job, and the discriminator tries to find the best weights for their job. And it's trained just as gradient descent, and as usual. And it's just here, the nice thing is that they go together, right? It's like one function applied after the other one. So you can still compute gradients for the joint thing. So to train both of them, they cannot be trained separately, right? They have to be trained together when they process here random noise goes in, and here a real data point goes in. And then in the end, the loss is if the discriminator was able to figure out if it was real or fake. And they generate super photorealistic images. So this is I should replace this by a newer paper, but yeah, so a few years ago, this was only like some kind of smaller resolution. Projector is kind of not so good anyway, so you won't see. But nowadays, in the last few years, this can be like megapixel or even more like photorealistic images. And there's many variants of it, which also try to combine this with other maybe site information you have, or it can also be sometimes combined to get representations, but typically it's about learning to generate data. Okay, that was the overview of unsupervised, and after the break we look at clustering, which is a bit more mathematical. Sorry if this was a bit fuzzy, but it was to give some ideas about unsupervised. See you in 15 minutes. Let's get started again. So in the second part today, we'll make it a bit more concrete about how we can do unsupervised learning, and to be a bit more mathematically precise. So we will discuss the precise formulation of clustering, and more specifically the k-means clustering, which is a very simple algorithm. I think actually maybe most of you have, how many of you have heard about clustering in general? I guess all of you. And how many about k-means? Oh, good, that's about half of you. So I'll go a bit quickly on the definition of the algorithm because it's quite standard, but then we will take a bit of time to discuss the properties and also understand a bit better what it's motivated by, and I'll mention a few applications as well. So clustering is the idea is super simple. It's just we do a grouping of our data points. That's the easy part. The tricky part is to say what is a good clustering and what is a bad clustering. So what are the quality measures? That's where it gets more tricky. And for k-means, this is really the most commonly used clustering algorithm. And it's quite nice because it will allow us to discuss this a bit more clearly on what its properties are and how does it work. So what it tries to do is to find a prototype for each group. So a prototype is meant that, so there are many data points in a group, but you want to designate like one representative of you, the students, or of any group here. The representative should be one data point, or it can also be maybe an artificial data point derived from the other ones here. That doesn't need to be a real data point. We just use the midpoint, the mean of the group. That's what we use as the representative. So that's natural. And then the other thing is to have this assignment. So every data point n is assigned to a group k, and we have from 1 to capital K many groups. So these are the means, the mu's, and the assignments, the z's. So that's all the objects we have. And of course, there is the original data set. We have n data points. We want to put them into k groups. We assume we already know, we have decided it should be k of the groups. We just need to figure out who should belong to which one of them. So there is also, we actually prefer to write the assignment set as a, so here set n is kind of a one hot vector, which means it has a one where you are assigned and everything else is 0. So set n is asking where are we assigned? We are data point n. Which cluster k are we assigned to? So that's, you can say that is you just put a 1 where you're assigned, then you have a k vector. Where you're not assigned is 0, where you are assigned it's 1. And then you, the same thing, this is just saying the same thing as I already said. So if you do that, then you basically have made an assignment matrix. And that assignment matrix is just, it's 1 if you as data point n are assigned to k. So data n assigned to cluster k, and it's 0 otherwise. To k and 0 otherwise. So I need to work a bit on my writing. Okay, so this matrix has just a lot of zeros and a few ones. So this is the assignment matrix. So we don't know the perfect assignment, right? Our job is to now find this assignment. So, but we just, that's how we will parameterize it. And then here is the entire definition of the algorithm. It's actually an optimization problem. It's trying to find a good assignment. And here, what do they mean by good? So it's quite simple. It tries to, I'll give you the intuition first. It just tries that everyone's distance to their representative should be kind of small, and that's it. So you're trying to minimize the distance of everyone to their representative, right? And what does it mean, their representative? That's this mean vector mu k. We'll see in a minute how we define them. You just try to find some representative such that everyone belonging to that one is is close to the representative. And that's it. And now you just try to find, optimize this, right? Minimize this, the whole data set with these K groups has the smallest distance of everyone to their representative. Here is the assignment matrix, here is the representatives. Those you can, both can be learned by you. So that's the K-means optimization problem. But you need to respect this bunch of constraints. You need to respect that everyone should be only assigned to one group, and everyone should be assigned to exactly one group. So that's this thing on the assignment matrix has this constraint, right? That you, data point n, when you sum up all potential groups you could be, your assignment can only be one, right? So all the others you have to be 0. So you're only allowed to have 0 or 1 in these assignment variables. And the mu's, they can be anything. So mu is just a continuous vector, 1 representative per group, and that's it. So, okay. The optimization problem looks kind of easy if you just look at it. I mean, this is super easy. It's just a quadratic, right? So this is the nicest functions we can have. They're perfectly smooth and nice and easy to differentiate. So that's the easy part. The tricky part is the constraints. So this is nothing, right? They are unconstrained, but the green assignment variables, they are constrained. So this is actually a discrete optimization problem. So that makes it a bit tricky. So, and another question is, well, is this joint thing, is this going to be still a convex function here or not? We might also come back to that. But it's the task is clear that we need to find this mean vectors mu and the assignments z. Does that make sense? I haven't told you how to find them, right? I just told you this is the goal. So we want to minimize everyone's distance to the representative. Okay, then, so how to do it? Actually, bad news, you cannot. So, well, you can, but this is an NP hard problem. So the problem to find this assignment set and the mean such that this is all minimized, this can be super hard, right? So, I mean, this is it doesn't mean that every real world instance you encounter is going to be very difficult to do, but it means that there are instances where if you can solve that K-means problem, then you can solve every other problem in complexity theory of the NP class, which we know is quite a hard task. So this is bad news. So it's definitely not an easy problem. And the good news is that there's still very simple algorithms which do extremely well. And yeah, so why it's NP hard is because this is the discrete variables. Discrete variables are hard to optimize because it becomes an integer programming problem for those of you who have heard about that. So it can be hard, but in reality, it's often really easy. Also, maybe we don't care so much that we get the very, very best clustering. Maybe we're okay to get a good one, because anyway, it's a bit unclear what is a good quality measure. If someone gives you a clustering and grouping, how are you going to be sure that this is a good clustering or a bad one? So it's not an easy thing in practice anyway to decide on quality measures of clusterings. So maybe we can get good ones even if you cannot get the best one always. And yeah, even if this is hard, there's very simple algorithms to at least get good clusterings. So yes, I should have explained this double sum a little bit, but we will get back to this later, right? This part here is just why is it sum both over n and over k, right? So the sum over k is a bit strange, right? Because for every data point n, we just want to count once, how far is it from its center. So, but this is taken care of here because the assignment is always 0 except when you are assigned. So what's in the blue part here is exactly the distance, is only one of these distances of u, xn, to your assigned center. And the assigned center is the mu k, right? So only that k which you are assigned to. So this is it's just a fancy way to write the one distance of one point to the center. And we will come back to this when we discuss this. Actually, this is a very nice problem structure. It's actually the same as a matrix factorization problem as well, as we're going to see in a minute. So, okay, but first we want to talk a bit about simple algorithms to solve this. And maybe most of you know the simplest algorithm already, which is the k-means algorithm. And it's really nice. You just randomly initialize the centers mu. So means algorithm. So, and the assignments, how do you do the assignments? So there's once you have some candidate centers, then the assignment is super simple. You just assign everyone to that representative which is currently closest. And then maybe the representatives are not the final ones, right? Just the ones we have now. We can assign everyone to that that representative mu which is closest. So given all the representative, find the data assignment which brings everyone to closest. And then step 2, can we find better means? And we will see in a second how this is done. So the assignment step is step 1 is the assignment step. So we can see here. So what we have on the left here is the data points are not assigned yet. That's why they're green. And we like to assign them. That's why on the right they become red or green, or sorry, red or blue, which means they have been assigned to one of the 2 cluster groups. So the means here are, they're just randomly positioned, right? The means have just been given to you. You need to deal with them. They're not the best ones yet. So mean vector 1, mean vector 2 of the 2 groups. Everyone who's closer to mean vector 1 will be assigned to blue, and the other one will be assigned to red. So that's the assignment step, step 1. That's very simple. You just need to compute everyone's distance to both candidate centers, and then go take the one which is closer. So, and that's, if you want a fancy way of writing, is this is which of the 2 k's do you pick? The one which is closer to your xn, right? So that's the assignment step. Any question on this? Then we have the second step, which is the mean update step. So step 2, that's again very simple. So the second step is the update the cluster centers step, or I don't know how you want to call it. Update the representatives. So it's the mu update step, and the first step is kind of the z step, updating the assignments z. Okay, how do we update the mu? So now we have the blue group and the red group, and obviously you can see that the centers we had before are bad representatives of what we have. So you change them. Hopefully as we said very initially, you want the representative should be in the middle of the current group. And that's it. That's how you update the centers. So that's everyone from group K. That's what we have on the top here. Everyone gets averaged. So everyone's vector xn who is assigned to K, they get summed up and averaged. And the denominator is just counting a number of people or number of data points assigned to cluster K. Yeah, if there's any question on Zoom, I'll try to take it. Sorry, people on Zoom, please ask questions. I'll try to answer them. Okay, just a fancy way to say that everyone compute the average of their group, and that's the new means. Okay, and then if you just do this once, so then now these are the new centers. It seems already better, but then the trick is to do this not only once, but repeat these two steps many times. So here is what I said. Now the blue mean and the red mean have been adjusted to be the center of their groups. So that's all, and we will maybe study a bit more how this really works on an example, and you also can do this on the lab, but you will only get this one next week, so you have time to. But then we also get the same data set as we have here. That's also for you to play with the lab. Any question on this one? Then what I want to just briefly discuss is how expensive is this algorithm? So, oh, sorry, there's a question. Can we get stuck? Excellent question. So, yes, we can get stuck. This has, yes, it depends what we mean by stuck, right? But actually, I will get back to this, yes. So at some point, the assignment will not change anymore, but that's usually when you will stop the algorithm. And then the question is where you stopped. Was this the best clustering you can get, or did you just stop in a local minimum, so to say? So we will get to that. Yes, you can get stuck. But okay, so that means I cannot tell you how many steps of this do you need, right? Until it stops, or until you're stuck, or until you find the best optimum. We don't know. But what we surely do know is how much do we pay for one step. So maybe this is a question for you. So order of how many operations do we need to do one step here? So here, this is the Z step to find the assignment. Here is the definition of the Z step. Find everyone's closest representative. Any suggestions? How many operations? So there's K groups, there's N data points, there is D dimensions. So these are two vectors in D dimensions, and there's a bunch of candidates. How would you do this naively? I hear K, D, and that's per data point. So also, okay, so for one point N, how do we find the closest center, right? You just compute the distance to all centers. We actually said this. And then you take the one which is shortest. So here, this is K candidates. You need to compute the distance to. So this is a K times D, as you said. But then you have to do this for every N. So it's N times K times D. Do people on Zoom agree?
Does it work in very high dimension?
Does it work in high dimensions? Yeah, it works perfectly fine, but the same caveat appears. I cannot give any guarantees that this is going to go to the true optimum, right? So, but yeah, having higher dimensions is usually not a bad thing. It means you have more freedom. So it should work fine. So, how do we initialize the center points? That's also a really good question. There are a lot of research papers on that. It's also tricky. I cannot give a good answer, because if you already imagine you initialize the centers already close to what would be the best assignment, then you were lucky, right? And then you would even go to the true optimum. But it's hard, right? I mean, whichever algorithm you have, which you think is your favorite clustering algorithm, you can actually use that to find good starting points for this one, for k-means. So if already someone gives you a grouping, then those means, you could use them here as a starting point and then see if the k-means algorithm would improve the clustering even more, or maybe not, maybe it's stuck, but there are of course many clustering algorithms, and every clustering algorithm will produce an assignment. Yeah. So here we just talk about the easiest kind of, or this type of easy algorithm. Okay. Yeah, these were two side questions because you guys don't like to compute these complexity numbers. So, but we have one more to compute. We need to compute how expensive is it to update the means, the second kind of step. Any ideas about that? So I have k of these mean vectors, need to compute them. Yes. Yes, you said n times k times d, actually the same as we had before, and that's correct. So because yeah, you have to every data point has to be summed up, right? I mean, it depends. This is how many people are in this in each cluster, but overall, every data point has to be summed for every cluster. Maybe there's some small optimizations that can be done, but naively, it's this. So this is. It's okay, right? It's linear in every parameter, linear in number of points, linear in dimension, linear in number of clusters. So not too bad, but if all these numbers are big, then it's not going to be easier. So, okay. And then we come a little bit to your question if we get stuck or not. So what's interesting is if you do this, then at least every iteration, you actually make this loss function a bit better. So that's nice. And by loss function, I mean the thing we defined here, right? That we said this would be the ideal. We want to minimize this function, but it's very hard. But in every step, you bring this a little bit lower. In every step, you make small progress at least. So it decreases the cost, the L of, depending on the assignment and the means. So you make progress in every step. So you go down, 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 and then you stop. But it doesn't mean that you might be at the true optimum yet. So we don't know, right? So you might stop here. So I'm not able to give any proof if this goes to a local minimum or to a global minimum. So this already suggests that maybe this function is not convex, and actually it is not. Yeah. Okay. And what is happening here? Actually, there's a one other nice way to see it. To again connect a bit better to what do we want to minimize. So what's happening? We said we want to minimize the L, and what we're actually doing is that first we update the Z and then the mu. This is these two types of variables, and you can see this as a coordinate descent method. Which, what does it mean? It just means that one group you fix, you don't touch, and the other group you minimize. So that's what coordinate descent does. And here it's over the whole block of coordinates. So we said this is a bunch of variables, but the point is that we only optimize over Z, and the mu we keep it fixed at the current step. And then in the next step, so in the next step I do the opposite. I'll do it for the means. So in the second step I will do it for the means, and the means are green and the assignments are something with these colors. So the idea is you only optimize the assignment in one step, right? So and that can be seen as completely minimizing this function, or it can be seen as doing a few gradient steps, maybe only on this Z variable, and then when you update the means, you only touch the mu variables, and those actually you completely optimize. So if you want to think about this, then you can see that So if you do this perfectly, so perfect minimization of mu, then you have the means update, the mu update of k-means. Because it's the best you can do. So there is no better thing to place your means if the assignment is fixed than to make them actually be the average of each group. There's no other, it's just a geometric property. The point which minimizes distance from everyone is actually the point which is in the middle. We have seen this, right? We have seen this in the one-dimensional case as well. Then, yeah, which point is closest to everyone? That's when we did the L1 loss function. Then, sorry, L2 actually. Well, it doesn't even matter. It's the solution to both of it. Who is closest to the whole data set? In L2, that's the mean if you're in one dimension. And also, if the distances are summed up, then it's the mean of this group of points, which is this point cloud, which represents one group of your clustering. So that's for the mean update. The assignment update is a bit more unclear, like how much progress do you get when you change the assignment? This is harder to say, so we're not making any claims there. Also, it's discrete, right? It's not, we can't just do a gradient step. But here, things are nice, and we perfectly optimize the mu. So, okay. So, I mean, it's nothing here, right? It's just saying this algorithm you have seen, it can be interpreted equivalently as coordinate descent, which is kind of natural. So then what we should also not forget is how do we find the number of groups k? Is there a good way to choose k? How many groups? That's actually also quite a difficult question. So how to set k? And there's not much rigorous theory that I'm aware of how to set a perfect k, which we can justify that it's a good choice, right? Because it's not so clear what the quality measures are anyway. What are good clusterings? What are bad clusterings? So if you just look at the loss, the one we defined, right? This is just everyone's distance to their representative. Then, yeah, what do you think then? If you just say which k will give me the smallest loss, which k do you think would be best? Yeah. A second k. K, yeah. You say k equal n, as many groups as you can. That's correct. Yes, yes. The more groups is always better. It's kind of intuitive, right? You have a grouping, and then I can just make these distances smaller by taking one of your groups, cutting it in two, or make one of the points in the group be its own cluster. Then that point has zero distance to its representative. So more groups is always better in terms of loss, right? But it doesn't mean that it's a good clustering. Of course, everyone being their own group is not a good clustering. So, but it's hard to mathematically say why and what you mean by good. So what you will observe is usually something like this, that the loss surely goes down with increasing k. And at some point, as you said correctly, maybe here you have a, so, okay. So here something crazy happens. That's what you said. If k equals n, then the loss is actually zero, right? Because nobody has any distance from its center. So yes, a larger k is always better in terms of loss, but it doesn't mean that it's a good for anything real. So you want to be somewhere in the middle, but not clear where. So it depends on your application. Maybe it really depends. Yeah, what you use these clusters for, right? So maybe you develop this clustering for a certain application in a company or so, and they have capacity to manually look at 11 groups, because otherwise it costs too much money. So that's why you would choose k equal 11 for that. Or so maybe cost can be an issue, or maybe what you want to do afterwards with that clustering might be better or worse with this number of groups. So yeah, in the end, it's just a hyperparameter. We cannot say much. It's your choice how to choose it. There is one small thing I can maybe mention, is that often you do observe some kind of elbow phenomenon, which means if you look at this plot here, loss versus number of clusters, sometimes you see something a bit like this, that it goes down very quickly at the beginning, and then at some point it starts to go down slower. So that's actually an interesting choice of number of groups. That's not the only way, right? It really depends on your use case, but sometimes there is a phenomenon like this, and sometimes then this could make sense to say that this is a bit a more natural grouping than others, right? If your data is naturally clustered like this, so if all the data points are really in this and there's no point outside, then it would be very kind of strange to have like one more cluster. There's sorry, that's not the correct image. So it would be strange to have a point inside this group to be its own cluster, because there is kind of a natural grouping. And then if you make this guy its own cluster, then the loss will go down only more slowly. That's the intuition. What would happen if you're here? So, but it's not always so clear, right? In reality, the grouping will look a bit maybe more chaotic than this picture here. So, okay. So that's about k-means, and maybe we go through. Yeah, this I let you do yourself. So this is the data set you also have in the exercise next week. You can see what happens when I do an assignment step. Group colors change. When I do a mu step, I update the means. Then you can see this means change, of course. And then again, so you just alternate between assignment steps, mean steps, assignment steps, and so on. And you can see the clustering becomes more and more natural. Like here, it was surely not a natural assignment to colors. And here, the further down we go, the more natural the clustering looks, actually. So, and then when do we stop? So that's something we need to discuss, to come back to your question on when do we get stuck? Yeah, we do get stuck. That's what you see here. So in this situation here, you found your new means. Now you're trying to find a new assignment, and turns out nobody has changed color. So none of the points changed from blue to red. So here we have no change anymore, no change in the Z. In Z. So if there's no change in the Z, then the means I had before are going to be the same as I will have now, right? The means will also not change anymore. If nobody has changed the group, then the mean of each group remains the same. So that means there is also no change in the means in the next step. So we have stopped the process. Whenever this happens, then you stop. So whenever your assignment stops changing, also the means will stop changing, and then you're is stopped forever. Usually it stops in a good clustering, right? So what we see here is it looks good, right? But it's not so easy to give a mathematical definition to say that this is the best one. And in the sense of the mathematical way to say if this is the best or not is the one we saw on the first slide, right? Does it minimize the optimization problem? And this we don't know, right? We only know that this particular k-means algorithm stops. And it's a really good algorithm. And usually, most cases, it really gets you to a loss function super close to the best you can have. And furthermore, the clustering it finds are very useful. So that's k-means. Try it out in the exercise. I will just give two more small things. One is a bit on to say what is it useful for, just one natural use case. And then we finish by telling you that k-means also has a probabilistic interpretation and a motivation. It makes sense to use this objective function. Why did we use this objective function at the very beginning? It was unclear, but this will be answered at the end. So, but first, a small application, and it's data compression. So it's for images, but you can do similar things for any type of data. The idea is that every feature can have many possible values, right? For images, the value is the color. There are 10,000s of colors, actually 16 million, right? People usually use how many colors can each pixel can have this many colors. So if you store each pixel as this 16 million, a lot of bits and bytes, then that's very expensive, right? That's why images are so big on the hard drive. So can we use clustering to represent images more efficiently? So this is a very, very naive way to do a feature compression. So, and the way it does it is just to throw all the pixels into a bin. Every pixel has actually has 3 numbers. So let me write what a pixel is. So xn is consisting in these 3 values, which is red, green, and blue. And this takes a lot of space, right? So I don't want to store all these individual values. So can I make groups of pixels? That's what we're doing here. So lots of pixels. So for example, 100,000 data points. That's what you will get if your image is 200 by 500 pixels. Okay, so maybe it's a bit confusing here. There is only one image, right? But this one image gives us 100,000 data points because every pixel is a data point. And now the pixels will be put into groups, and what we use is the distance here, that the distance in color, right, from each pixel to the others in the group should be small. So just to k-means that everyone in the group will have their representative color. So that's what you will get when you do this, because every group of pixel, the mu of that group will be the average of these everyone's 3 vector, right? So xn, everything is in R3, right? Every data point is in R3. Many pixels have similar colors. They end up in the same group. And then I just replaced all these pixels. I just replaced them by their mu. So the xn's will be assigned to the mu k, and mu k, of course, is also a real thing. But the good thing about mu k is that there are only k of them. So there's much fewer colors to store. So, and yeah, this can take this quite to the extreme. If you only take 2 colors, so then the image is still kind of recognizable. Not perfectly, but still, it could be worse. If you take k equal 10, this many groups, this many colors, then it looks pretty realistic. So you can say that instead of having 16 million values per pixel, now you only have 10 values per pixel. So you have made a huge compression. And it's not the best image compression, right? But it's probably the simplest one you can do. It's also really fast to implement it and to use it, right? So, and actually GIF images, they use some variants of this as well, but some smarter additions as well. So this, when you do clustering on these pixels, that's called vector quantization. Any question on this? No. Just a simple use case. Okay, then there is a small thing I want to tell you, that there is also makes sense that we use this loss function. So there is actually the loss function we defined has a very reasonable meaning, and actually the meaning that it has is to have the maximum likelihood of the data for our probabilistic model. What's the model here? It's just that there are k groups, and we will see that if you generate data from these groups, and the groups, each group is a Gaussian distribution, then you will actually get that the likelihood is the k-means objective. So that's what I want to prove for you. But this is only true if the data comes from a normal distribution. So every data point is normally distribution around its own group, right? Around the mean k where we are assigned to. And that the Gaussians are spherical. So there's no ellipses, right? Just spherical groups. Every group is a Gaussian, and U, Xn come from group K. So then that's the likelihood, right? Probability of X given that you come from cluster K. So, but which cluster? So I can rewrite this. Nothing happens here. I just rewrite that the cluster we are assigned to, that is actually described by the assignment. So I just use the assignment notation to make clear which K I'm not talking about. And now this might be a bit scary. So I write this in the exponent. I write the probability of X taken to the Z and K exponent. That's a bit strange. Well, it's actually easy because these assignments are 0, 1. So it just means there where you're not assigned, it's canceled anyway. Nothing is here. Only the assignment where you are assigned, which is a 1, only that term will count. So that just to convince you that I've done nothing. I've really just written the same thing, the likelihood of point X coming from cluster K. Then I will plug in the definition. What is a normal distribution? So it's some constant times e to the distance from the center, right? So here it's simple. It's just going to be the Euclidean distance, x minus mu, because this is a spherical Gaussian. There is no covariance matrix, so life is much easier. And then it's taken to the Z and K exponent, right? But that just becomes a product here, because this is already the normal distribution already is an exponential. So that's the assignment. And the mu's are here. Okay, and now, okay, this looks scary, but we're basically finished. It already looks a little bit like the k-means objective, except there we don't have products, we have sums. And also, I don't want to just talk about one point. I want to talk about the whole data set. So that's P of the whole data set X, given all the means and all the assignments. And of course, when having one point is this likelihood, having all these data points be what they are, then you have this n random things happening together, which then means every data point, of course, is sampled uniformly, independently from the others. So that's why we have a product when you ask about the whole data set. 1 to n, product over n, product over n. Still looks very nasty. But then if I take the log of this, actually I will take minus the log. Then the products disappear and become sums, and then we are done. And then we really have the k-means objective. And that brings us to the end Just the two products have become sums when I take the log. And what you see now is really the k-means objective. Everyone from their center mu is kind of close. And there is a plus a constant here, which you don't need. So this thing here is exactly the loss function we had at the very beginning when we said k-means means to minimize loss function we originally have about the means and the assignments. Okay, this is to motivate. Why this loss function, right? Because if your data is coming from normal distributions for each group, then this means to maximize the likelihood. So you find those centers, mu, and those assignments, z, which maximize the likelihood, which make it most likely that the data we observed has come from this particular mu's and z's. So that's why the k-means loss function is a nice loss function. And I think that brings us to the end. I'll take 2 minutes next week to tell you that k-means is a matrix factorization, but it's very easy. And that's it. And then we see a generalization of k-means also next week about Gaussian mixture models. So see you next week.